If you remember, yesterday we said professional link has improved significantly. Now we don't go serial, but we sit around the table and talk. All the discipline experts and people working for the field development is talking to each other, cooperating, and discussing the issues and deciding together. It's not a serial. Okay, so this is called multidisciplinary integrated team. Okay, that's the work. And the question here, why do we need integration? Why do we need integration? Because the subsurface is uncertain. Okay, there are wells. Okay, at well locations we know the data, we have the data measurements, such as well top, the entry point of the reservoir is known at well locations. Okay, if we drill another well, we also learn the top of the formation at the new well. And all wells tell us where the reservoir starts, where it ends. If we don't drill all along the formation, we have the entry point like here, but we don't have the exit point. So we have the top marker, but we don't have the base marker. So it's an uncertain. So how do we understand, or how do we know where is the exit point? Okay, so all the wells has to penetrate all through the formation, but especially horizontal wells, because we are targeting to drill the reservoir. We don't go to the base of the reservoir, so we don't have the markers. And at interval locations, we don't know what is and how is changing the properties and structure. And at interval locations, we have a lot of question marks. All they are uncertain. We don't know. We don't get. That's why we need geophysics. That's why we need geology and engineering. All they have to work together to understand the sky, the reservoir better. Otherwise, it's going to be blindly developing the field, okay? And if you break the links between the departments, disciplines, only geologists work by themselves, only engineers work by themselves. So they look at the reservoir with only from one aspect. And that aspect is limited. So they have the limited understanding of the reservoir. So to overcome this problem, to see from different perspectives and understand better, we need multidisciplinary approach. Okay. So in integrated approach, we have the seismic attributes from the seismic, borehole geophysics, okay, because as I said before, the seismic resolution at vertical depth is not good. So that's why we need sometimes to calibrate the seismic data with the borehole seismic. So they send the geophones inside the well and they measure the signals. Okay, they record the signals and analyze it at well bore. That gives much better picture of the seismic. Okay, that's used for the calibration of the seismic data. So we have the structure and faults from the seismic. So this is the geophysical's understanding or knowledge. Then the geologist, okay? The geologists look at the outcrop. They look at the core data, okay? And then they analyze the cores to find what kind of rocks appear inside the reservoirs and how does it change from one well to another one. So the geologist is analyzing the core, and then they develop the understanding of stratigraphy. They get the logs from the petrophysicists, and the sedimentologists tell us the deposition, the rock type, facies, and the diagenesis, all the changes happening in the rock is by sedimentologists and under geological understanding and knowledge. Then we have the reservoir engineers. They test each well, and or they produce from each well. And production data or test data tell us the dynamic features, flow behaviors of the field, okay? And they measure the bottom hole pressure, reservoir pressure. So they measure the changes in the pressure, which tell us the transmissibility and the flow behavior of the reservoir. So all they come together to describe the reservoir, okay? So the ultimate goal is to get accurate description of the reservoir, okay? That's the key, accurate description of the reservoir. And we need integrated approach. All the disciplines work together. What is the benefit of integration between the disciplines? We reduce the uncertainty significantly, okay? If we look at from one perspective, our understanding is limited. If we bring the different perspective together, we reduce the uncertainty. And the environment that we bring different perspective is geological model. In that model, we integrate all the understanding, including the geophysicists, hydrophysicists, reservoir engineers. And we get, if we reduce the uncertainty, then we get the realistic description of the reservoir, more realistic, okay? And then reliable and accurate decisions can be made based on the realistic descriptions. If we said that our goal is to get the realistic description, right? If we get our data more than the actual, let's say porosity, okay? Our porosity is more than the actual porosity. If we get the permeability more than the actual permeability inside the reservoir, if we get the more volumetric, okay? What is this case? Is it realistic? What is it called? If we exaggerate of the reservoir properties, that's called optimistic description, optimistic case, okay? If we are exaggerating. Or the opposite way, if the discipline experts, specialists, they make the numbers, they calculate, okay, they predict the the parameters less than the actual numbers, okay? Let's say that in actual case, we have 27% average porosity in the reservoir, but the geologist or petrophysicist is predicting 22%. So 5% less than the actual cases. So what is this case called? If the numbers are less than the actual. So if it is more than the actual, we know that it is optimistic case. If it is less, it is pessimistic case, okay? So we have three cases: optimistic, pessimistic, and what is the third case, which is our base case? Realistic case, okay? So in between optimistic and pessimistic, we have the realistic case. So that's where we want to stay, okay? In realistic, we don't want to be too optimistic, too pessimistic, but in realistic. But the life is not that way, okay? So you have to make a prediction at the end, and that prediction may be more than the actual case or less than the actual case. That's why we need uncertainty modeling, uncertainty analysis. So this is the workflow of static modeling, okay? If you like to do geological modeling, you have to follow these three steps. Our first objective is to make a structural model, okay? Where you have your physical reservoir in the computer. You define where it starts, where it ends, okay? And how extended is your reservoir? What is the top structure? What is the base structure? What is the depth of the structure? And how the subzones are changing, okay? So you need first structural model, where you define your grids, geocellulars, cells, okay? After you define your structure precisely, where is the reservoir, wherever it is, you describe in computer with the numbers, XYZ coordinates, then you need to fill each cell with a property, okay? That's called property modeling. So you have the rock in every grid of your reservoir, every cell. And what is the property of that cell? What is the porosity? What is the permeability? What is the saturation? Hydrocarbon saturation, oil saturation, or gas saturation. What is that? So every grid, you have to define that, which is called property modeling, okay? And once you've done your structure and property model, then you need to analyze on your way of measuring or defining, predicting what kind of risks, what kind of uncertainty you have. You say that this is 20% porosity, but it may be 22 or 18%. So looking at the pessimistic and optimistic cases, you define your uncertainty envelope, which is called uncertainty modeling or uncertainty mitigation. Because once you understand your cases, low case, high case, and it gives you the envelope that you can go as low as this or as high as this, so you have to mitigate that envelope. You have to reduce it. Sometimes it's so big that makes difficult to make decisions because you don't know the case in the field. It might go very high or very low, and you don't know what is it. So how you make the decision? For instance, the field is far away from the center, from the nearby refinery. You have to put a flow line. You have to transport the crude oil that you are producing from the field to the refinery. And you need a flow line in between your field and the refinery. You have to put a flow line with a certain size. And what is that size? If you put too big, you're going to spend a lot of money for nothing. If it is too small, then you're going to try to produce more, but that flow line is going to be the limiting bottleneck for you. So you have to make a decision on flow line. It has to fit to your production. If you don't know how much you're going to produce, your uncertainty envelope is too large, then which size of pipe you're going to put, you don't know. And what kind of pumping station you're going to generate. You have to put a pump, hydrocarbon crude oil pump, with the right size. If you put too strong pump, you waste. If you put weak pump, you waste again. So all these things, okay, all these parameters, I'm giving you some examples, needs uncertainty analysis, needs correct, accurate estimation, okay? So there are a lot of parameters at the end of your study of your structural model, property model, you have to define, okay? You have to define in a way, gives you the production profile during next 10 years, 20 years, 30 years. Based on that, the field surface facility is decided. Surface facility sizes are decided, okay? So it is very important what you are doing in the static modeling. I'm not gonna go all these details, okay? Low core, well picking, isocore generation, and then the grid generation. Then you scale up. What is the scale up of the properties to the model? And then what is variogram? What is the histogram modeling, which is the geostatistical side of the property model? And then how you run your SGS or kriging or whatever. This is the modeling of the property into the model. And uncertainty, how you generate your low, high case, low case. So this is called multiple scenario or multiple equiprobable case generation. All these things are two details of the modeling steps, and then you have to analyze. In this course, our scope is the basic understanding of the static model. So geological framework is completed by layering. I said there is structural modeling, as you can see. You do the core, well picking, isocore, and then you make the layering. Then your framework is completed. And then what is next? So what do you see here? What do you see here? You see a big box, right? A big box. And then you see small cubes defined in it. And there is a point here, another point here, and there is a line, okay? You see, this is the well, and there's another well here. You see, it goes all along. So that's where we start. We start with the well data, okay? The story starts with the well data. So we have the wellhead here and the trajectory of the wells. What you see here is two vertical wells, okay? This might be deviated or horizontal or some kind of angulations in the well trajectory. So never ever drillers can drill completely vertical wells. There is deviation at the end. So after that, you get the logs and you define where does your reservoir start and where does it end, okay? So this is called markers, the formation top and the base. Then you define your reservoir top and reservoir base between these two wells. If you have three wells, each well has to be defined. Where does it start and where does it stop? So after that, you divide, okay, between the top and base, you divide by layering, okay? And you divide aerially the grids. So these are, each one of these cubes inside this box is one grid, okay? So if you have a fault in between two wells, so you have to put fault modeling, okay? Where the formation shifts upthrown or downthrown. So this is your fault, this is your model. Do you see any fault? No fault yet, because it's straight, the structure is straight. You see, this one, there is a shift, but there is no fault. This is fold, okay, with D. That's where your formation top goes down, okay? But this is fold, there's a shift, okay, which is called juxtaposition, yeah? So this grid has a face on the other side, another grid, but not face to face. All the rest of the grids are face to face, but there's a shift here. So this is called juxtaposition. So you see here with the fault model here, you define your grids, okay? Each grid has corner points, yeah? So how many corner points we have for each grid? 1, 5, 8, 10. How many? You see, if you look at this cell, this grid, there's 1, 2, 3, 4 corner points at the top and 4 at the base of this grid. So total 8 corners. So this 8 corners, X, Y, Z of each of them defines this grid. And each grid is defined in the computer with X, Y, Z coordinates. Of course, this is a flat reservoir here, which is called tank model. I generated tank model for your understanding, okay? But in reality, the top formation is not like this. There is no flat reservoirs, okay? There are highly complicated geographies, highly complicated geological structures. So this is simplification. So after you define your XYZ coordinate of each grid, you see the next step is to define the properties inside this grid. How the rock is porous, how it is permeable, Okay, what is the permeability? What is the porosity in each rock that we have to define, which is the next point. And that next step needs deep understanding of geoscience and has to use geostatistical techniques. And geostatistical techniques requires mathematical algorithm. And that's why we need a special software package. Okay, so all these things, geoscience, geostatistics, mathematical algorithms, is configured under a software package, and we use that package to run and obtain. There are a lot of video about petrel in YouTube. You can very simply search and find it. I'm not gonna go to those videos. I can show you how to find, but it's not the objective of this course. The objective is to understand the logic behind the static modeling, okay? And the logic, the main point is geostatistics. So you have to know geology along with the statistics, because as we said, at interval location between the wells, you don't know the properties, how it is changing. So you have to use statistical techniques to make a prediction. That's where the mathematical algorithms comes into the picture. Okay, so geostatistics is very important, and there are good resources in YouTube. Again, you can listen and learn. Okay, so as you can see, this is our tank model. We have a well here, another well here. At well location, we have log data. Okay, there's measurement at this well location and at this well location. As you can see, the rest of the grids are gray or white, but here pink color. And this is where our well, pink, blue, green, red, turquoise color. So this red color represents the numbers for this well. If you are looking at the porosity or permeability, so the color indicates a number. At this well too, okay? So that's why we are defining the rock property here at the well location by looking at the log data. Okay, because we have the data at this well location. So we can look at the data and say that this grid has 5% porosity by looking at averaging the log porosity, okay? By looking at the saturation, by looking at the permeability, we can say that the rock property here at this location, at this grid, by looking at the well data, this is it. Same thing at this well. If you have other wells all around, you can define your grids numbers from that well log, which is called upscaling of the log data to the model, okay? Model grids. So that's the step where you define your values from the well data. And after that, you have to go to your statistic at interval location, look at the statistical algorithms and define all the points, all the reservoirs. So that's called property modeling. Okay, so you see each grid has a value, and this is defined by geostatistical technique. There are different techniques you can call kriging, sequential Gaussian simulations, indicator kriging, or moving the average technique. So there are different techniques to identify the values in between the wells. That's why you need to know geostatistics. And this shows what it shows. It shows the porosity. Okay, red is 20%, blue is only 2%. Okay, this is the scale. And you see we have divided reservoirs into slices from east to west, north to south, and east to west. And we can look at, okay, how does it change in vertical here, aerially this direction or that direction. So this shows that the good spot is here or here, and relatively low porosity goes down. And as you can see, there is a subzone here after a certain interval. It is very tight, 2% porosity, okay? And it is all along the reservoirs. So this blue subzone is, you see, continuous, even it's here. and then it goes to the high porosity interval, and this is a very thick reservoir. At the top, there's a thin reservoir, goes very tight, then a porous reservoir starts. And the second reservoir is much thicker than the upper part. So you see, this is the analysis of property modeling all around the reservoir. What is the main problem? What are we after? Why we are doing all these studies, okay? Why are we developing a model and then making a simulation? And what is our problem? All these efforts and all this work, why is it happening? Because we are trying to deplete the reservoir with a high recovery factor, okay? You can omit all these steps. You don't care the geology, geophysics, reservoir engineer. You can just simply drill and produce as much as you can. And if the well starts producing water, just close the valve and go to another one. You can do this. But if you do that, blindly develop your field, okay? Without knowing what's going on, what kind of reservoir you have, you kill your reservoir. You kill a reservoir with a very small recovery factor. What is recovery factor? Recovery factor is the amount of oil on the surface you can produce to the whole crude oil volumetrics to your reservoir. Let's say that reservoir has 100,000 barrels, okay, initially in place when you discover the field, the reservoirs. So when you start producing, you cannot produce 100%. You cannot produce 100,000 barrels of all the reservoirs because of different geological features, because of water coning and so forth. How much oil you can produce? You know, maximum 30%, 35%. Maximum, if your reservoir is very porous, very permeable, high permeability, you can go maybe 35, 38, up to 40% if there's aquifer support, okay, pressure support. Even the enhanced oil recovery, tertiary oil recovery, maximum recovery factor is 35 to 38%. Where is the remaining 70% of the oil? It's inside the reservoir, but you cannot produce. So that's the real problem. That's the challenge. That's why we are doing all these work and studies to increase the productivity as much as possible and to reduce the cost as much as possible. So with minimal cost, maximum productivity is the objective of all our study. Otherwise, it's going to be a blindly development and killing the reservoir. Maybe you will be able to produce only 10%, 5% of the reservoir. And the remaining is going to be inside the reservoir, hiding from you if you don't chase it, if you don't study on it. So that's the challenge. So as a result, we are saying that multidisciplinary integration is causing, okay, the benefits of that is certainty is increased by the constraining models with all available data, properly looking at the data, generating a development plan with the certainty, with understanding, well understanding, and then reaching the realistic reservoir description and looking at even your probable high case, low case, and considering in your development plan, if you produce higher than what you are predicting, what you are going to do. If you cannot produce as much as you wanted, what you are going to do. So that's the uncertainty mitigation, okay? Risk management that you have to learn and tackle with it, okay? So reliable and accurate decision is objective. That's our objective. We have to have a reliable model, reliable dynamic simulation that we rely on with our accurate decisions. You make the decision, you make the recommendation, But if it fails, that's the bad thing happens to you. Okay, so you have to have a good model which is reliable, that you rely on, and your management relies on you, on your work, on your results, and you make the accurate decisions. Okay, so that's good. So this is all today. Tomorrow we are gonna start working on the data. Okay, let's start working on the data tomorrow. All right, have a nice day today. I'm gonna make some posting in LinkedIn, and please make comments. Okay, I need to see your comments over there. Thank you.